Hello everyone. Today we are presenting our SC6019 course project, Payment Upchain built on OpStack. This project explores how a layer-2 application-specific chain can support low-cost and high-frequency payment transactions. Our implementation includes a local OpStack-based payment upchain, smart contracts, a front-end dashboard, and initial benchmark results. The motivation of this project comes from the limitations of general-purpose blockchains. On a shared public chain, payment transactions compete with DeFi, NFTs, gaming, and other applications for the same block space. When congestion happens, users may experience unpredictable gas fees and confirmation delays. This is especially problematic for small value and high-frequency payments. In contrast, a payment-focused upchain provides dedicated infrastructure for payment transactions, which makes the payment experience more predictable and easier to optimize. Our project has three main objectives. First, we deploy a local OpStack-based Layer-2 payment upchain and provide an RPC endpoint for front-end and contract interaction. Second, we implement the payment utility using Mockist as the test payment asset and payment ledger as the main payment contract. Third, we build a front-end interface where users can connect MetaMask, approve token spending, send payments, and view payment records. Together, these components form the MVP of a payment-focused upchain. This slide shows the overall system architecture. At the top, users interact with the application through MetaMask. The React front-end provides the payment interface and connects to the local L2 RPC. On-chain, we deploy two main contracts, Mockist, which acts as the test stablecoin, and Payment Ledger, which handles merchant payments and payment history. These contracts run on our OpStack payment upchain. The L2 chain uses chain ID 66109 and exposes a local RPC endpoint at localhost port 8545. Ethereum Sepolia is used as the Layer 1 environment for the OpStack setup. The payment upchain uses several core OpStack components. OpGeth acts as the execution layer and processes L2 transactions. OpNode handles the rollup node logic and coordinates sequencing and communication with the execution layer. The Batcher and Proposer connect the L2 network with Ethereum Sepolia by publishing transaction batches and output routes. Together, these components allow our local payment upchain to process transactions while following the OpStack architecture. The on-chain logic is implemented through two smart contracts. Mockist is an ERC20 test stablecoin with 6 decimals, similar to real USDC. It is used as the payment asset in our demo. Payment Ledger is the main payment contract. It processes merchant payments, applies an application-level fee, prevents duplicate orders using order IDs, and records payment history for both users and merchants. This design makes the payment flow transparent, auditable, and queryable on-chain. The payment ledger contract uses a simple percentage-based fee model. The default application level fee is 0.1%, or 10 basis points. The contract also includes a maximum fee cap of 1%, which protects users from excessive fee settings. For example, if a user pays 10 must-see, the application fee is 0.01 must-see, and the merchant receives 9.99 must-see. This fee model is simple, transparent, and predictable, which is important for small value payment scenarios. Next, we introduce the front-end dashboard. The front-end supports MetaMask wallet connection, real-time must-see balance display, payment form input, fee estimation, payment history, and a merchant dashboard. The payment flow follows the standard ERC20 process. The user first approves token spending and then submits the actual payment transaction. Now we will demonstrate this flow in the recorded demo. This first demo shows the complete payment flow from the user side. The user connects MetaMask to the payment upchain local network, enters the merchant address, payment amount, and memo. The front end automatically calculates the application fee and the merchant's net received amount. Since Mockist is an ERC20 token, The user first approves the payment ledger contract to spend the token. After the approval is confirmed in MetaMask, the payment transaction is submitted through the front end, and the payment record appears in the dashboard. The second demo shows another payment interaction and focuses on the merchant dashboard. After the payment is submitted, the dashboard updates the total number of payments and the net amount received by the merchant. The table also records the payer address, merchant address, payment amount, application fee, and memo information. This demonstrates that the front end is not only sending transactions, but also reading on-chain payment history from the payment ledger contract. Together, these two clips demonstrate the complete end-to-end payment flow: wallet connection, token approval, payment execution, on-chain record keeping, and merchant-side payment history display. This slide summarizes the full transaction lifecycle shown in the demo. First, the user connects MetaMask through RainbowKit. Second, the user approves payment ledger to spend MACHist. Third, the user executes the payment by calling the PayMerchant function. Fourth, payment ledger records the payer, merchant, amount, fee, timestamp, and memo. Finally, both the user and the merchant can view the payment record through the front-end dashboard. At the current stage, we have implemented the core MVP of the project. The local OpStack-based L2 upchain is configured. MACHist and payment ledger are implemented. The front end supports wallet connection, the payment form, merchant dashboard, and payment history. We also completed an initial benchmark comparison. For future improvements, we plan to run larger-scale workloads, improve the Sepolia comparison under more balanced network conditions, add benchmark visualization, and deploy the system to a cloud environment. For the initial benchmark, we compared our local payment upchain with an Ethereum Sepolia baseline. The local payment upchain achieved around 16 to 17 transactions per second, while the Sepolia baseline achieved around 1 to 2 transactions per second. The average confirmation latency was reduced from about 11.68 seconds on Sepolia to 441 milliseconds on the local payment upchain. The estimated transaction cost also decreased from around 12 cents to around 0.2 cents per transaction, assuming ETH is priced at $2,000. One important caveat is that the Sepolia success rate was affected by Alchemy free tier rate limiting during testing. Also, L2 gas usage is higher because payment ledger executes RC20 payment logic, while the L1 baseline is a simpler transaction. Even with these limitations, the initial results show that a dedicated payment upchain can provide lower latency and lower estimated transaction cost for high-frequency payment scenarios. To conclude, our project demonstrates a working MVP of a payment-focused upchain built using OpStack. We implemented the local L2 infrastructure, MACHist and payment ledger smart contracts, a predictable application-level fee model, and a front-end dashboard for wallet-based payment interaction. The demo shows the complete payment flow, and the initial benchmark results show the potential of a dedicated upchain for lower latency and lower cost payment transactions. For future work, we plan to extend benchmark testing with larger workloads, avoid RPC rate limits for cleaner L1 comparison, integrate real-time dashboard visualization, deploy the system to a cloud or distributed environment, and explore RC for 337 for improved user experience. Thank you for watching.